Good day, grade 10s. In this lesson, we will investigate amplitude and frequency of the sound wave and how these relate to loudness and pitch. Nellie will show us how she uses an oscilloscope to investigate the amplitude and frequency of a sound wave.
Amplitude is defined as the maximum distance that a particle in a medium is displaced from its rest position. It is a length measurement given in the SI unit meters. Once again, it is much easier to measure the amplitude of a transverse wave. You simply take the distance from rest to crest. With longitudinal waves, it is nearly impossible to look at the medium and find the amplitude. Luckily, technology has come to our rescue. This machine is called an oscilloscope. It detects the compressions and rarefactions of longitudinal waves and translates them into an electric signal to produce a graph of distance against time. This distance reading on the vertical axis gives us the amplitude of the longitudinal wave. Please don't get confused now and think that because this graph looks like a transverse wave pattern, that sound is actually a transverse wave. It is not. What we see here is a graph, and sound is definitely a longitudinal wave. But when we investigate the way in which this machine picks up the difference between the rarefactions and compressions of longitudinal waves, we find yet another very interesting property of sound waves. Longitudinal waves, like sound waves, are also called pressure waves. You should remember from what you have learned about gases that when air particles are compressed in a small volume, they exert greater forces on each other and their surroundings, which in turn results in high air pressure. When the volume that the same amount of particles occupies is expanded, the force weakens and the air pressure drops. The same principle applies in longitudinal waves. When the particles are pushed close together, they exert stronger forces on one another. This causes high pressure in the compression area of longitudinal waves. Because the forces between particles are weaker when they are further apart, rarefactions are areas of low pressure. When a detector, like the oscilloscope, is used to detect a sound wave, it detects change in pressure as the sound wave strikes the detecting device. At one instant in time, the detector might detect a high pressure. This would correspond to the arrival of a compression. The next instant, the detector might detect normal pressure. And then finally a low pressure would be detected, corresponding to the arrival of a rarefaction. The detector doesn't have to be an instrument like an oscilloscope. As a matter of fact, our ears detect sound in exactly the same way. The membrane of the eardrum starts vibrating as the incoming pressure waves reach it. A compression forces the eardrum inward, and a rarefaction forces the eardrum outward, and in so doing vibrates the eardrum at the same frequency as the sound wave. Because the eardrum is connected to the hammer, the movements of the eardrum will set the hammer, anvil, and stirrup into motion at the same frequency as the sound wave. Since the pressure wave striking the large area of the eardrum is concentrated into the smaller area of the stirrup, and because of the denser medium, bone, that the wave is now moving through, the force of the vibrating stirrup is nearly 15 times larger than that of the eardrum. This feature enhances our ability to hear the faintest of sounds. Keep in mind that even though the sound wave is refracted in the denser medium, and for sound this means that it is sped up, the frequency of the wave remains constant. This is important because certain regions of the thousands and thousands of hair-like nerve cells that make up the organ of Corti has a natural sensitivity to a particular frequency of vibration. When the frequency of the sound wave matches the natural frequency of the nerve cell, then the nerve cell will start to vibrate with larger amplitude of vibration. This in turn causes the cell to release an electrical impulse which passes along the auditory nerve towards the brain. The fact that different nerve cells respond to different frequencies means that there is a special link between the frequencies of sound waves and the way in which our brains interpret sound. Let's use a frequency generator and the oscilloscope to explore this link by doing a very simple experiment. I have set the frequency generator to vibrate at 5 Hz. If I increase the frequency to 200 Hz, what do you hear now? If I now increase the frequency to 2000 Hz, describe how this sound differs from the last one you heard. Do you agree that at the higher frequency, the sound was sharper than the sound at the lower frequency? We say that this sharp sound has a high pitch. So this is the link between how we perceive sound and the frequency. The higher the frequency, the higher the pitch. The human ear can only detect frequencies between 20 Hz and 20,000 Hz. And that is why you could not hear the first frequency that I played that was at 5 Hz. While we have got the apparatus handy, why don't we explore another wave characteristic that is linked to the way in which we hear sound waves? Think about this question. What would change if we turn up the volume? Do you see that the reading on the vertical or distance axis increases? Do you remember that we said this shows us the amplitude of the wave? So, the greater the amplitude of the wave, the louder we perceive the sound to be. Why is this? Well, the more work done on the source to create the sound wave, the greater the displacement of the particles in the medium, and therefore the larger the amplitude of the wave.
So, to summarize what we have learned, the amplitude of a sound wave is directly proportional to the loudness. The greater the amplitude, the louder the sound. We have also learned that frequency is directly related to the pitch. The higher the frequency, the higher the pitch. Grade 10s, you'll find more information about sound at www.mindset.co.za/learn. Remember to try some of the questions in the task video too. Goodbye.